Yeah. In yesterday's class, we just started with the optimization, optimum design problem formulation, and we just revised what we discussed in the 15 days back. The different steps which are involved in the procedure. And of course, I discussed everything in detail in yesterday's class also, just to, in order to have a revision of the things what we discussed in the regular class. And also, we just started with one simple problem yesterday in the design of a CAD, how we can use the procedure, how we can use the formulation procedure for a different real life application. Okay. So before I just start with the problem, different problems today, I need to discuss some more things regarding the concepts of optimization. Right. So first, we start with yesterday. I was talking about the constraints. The last part or last step in the formulation of optimization problem procedure. We discussed what is a constraint, and also we discussed constraints, how to form a constraints for one simple design of a cantilever beam, and also I just extended that for one simple problem in the design of a can also. So before I just start with the further numerical problems, let us have a little bit of theoretical part to be discussed today. So just to understand some of the terms which we quite regularly we use in our design optimization. In such words is called constraints, which is linear and non-linear constraints. This yesterday we discussed constraints means it is just a what we call it as a restrictions that we want to impose it on the problems. And these constraints might be of different types. I was just talking about equality and inequality constraints in the last class. And a lot of that also we just have a brief discussion on equality and inequality constraints and expeditious constraints. And another type of constraints is the linear and non-linear constraints. So what is this linear and non-linear constraints means? So when a constraint functions which have only a first order terms in the design variable. So in the yesterday's class, we discussed what is a design variable, and also we have discussing how the constraints we have used in the design of a cantilever beam as well as the design of a can. Many constraint functions have only a first order terms in design variables. We call them as a linear constraint. So in the sense, when the relationship existing between the constraint function and the design variable. So in yesterday's class, we was talking about design of a cantilever beam. So where width and thickness, or width and width and thickness are the two design variables we defined yesterday. And these two design variables are connected to the constraints. So basically, the constraint in the design of a cantilever beam or a design of a can, we have a certain constraints we have discussed yesterday, and how these constraints are related to the design variable. So we need to equate or inequate, we need to relate the constraints with the design variables, and that relationship is in the order of first order. Then such kind of constraints we call it as linear constraints. And linear programming problems have only linear constraints and objective functions. In the sense, so we have two types of problems in our optimization problem. One is called linear programming problems, and the other one is a non-linear programming problem. So when you come for a linear programming, so all the constraints and the objective functions will be having a linear relationship with the design variable. So this is what we call it as a linear constraints, means constraints having only a first order relationship with the design variable. Just like you will have a straight line equation y is equal to mx plus c. So this is just a linear equation where y depends only on the x, which is have a linear relationship. In a similar way, if a first order relationship is there with the constraints as well as the design variables, then such kind of constraints we call it as linear constraints. In a similar way, non-linear constraints where the relationship between the constraints and the design variables is more than the first order, means higher than the first order. So it may be in the second order or third order. Then the such type of constraints we call that as a non-linear constraint. So only the differentiation between linear and non-linear is based upon the relationship existing between the constraint function and the design variables. Please remember, this is a very important thing. Why I'm talking here is we need to classify the optimization problems based upon linear constraints and non-linear constraints. So what we generally call it as the linear programming problems and non-linear programming. This is a one type of constraint what I would just wanted to talk to you in today's class. And second important thing here is the feasible design. We are talking about feasibility, feasible design, and all those things. So, what actually you mean by a design or feasible design? When we call the design is feasible, so basically, a design of a system is a set of numerical values assigned to the design layer. Means, if you want to design any system, so which, for example, yesterday we were talking about the design of a cantilever beam, where the design variables were width and thickness. And of course, similarly, in the design of a can, the design variables were diameter and the height. So ultimately, what we say the design of a system or design of a can or a design of a cantilever beam is the values what you will go to obtain, either for a cantilever beam in the form of a width and thickness, or in for design of a can, it is a diameter and a height. Ultimately, what the numerical values you will going to get it for the design variables, then that we generally call it as a system. Okay, even if the system is absurd, means it is having a negative radius or inadequate in terms of its function, it can still be a design. Understand? Please understand this. This statement is very important for you. If this design is absurd, even if this design is absurd or inadequate in terms of its function, it can still be a design. Clearly, some designs are useful and others are not. So design may be anything. So finally you are going to get a value. So, but that value, what you will going to obtain, whether it is acceptable or not, that is the most important thing for it. So when do we say the numerical values or the design of a system are acceptable? When it satisfies your requirements. So when it satisfies the constraint, everything needs to be satisfied. Then we will say the numerical values what you have obtained or the design what you have obtained is acceptable. So if design meeting all the requirements is called as feasibility. This is what the important thing what you should remember. Well, because quite often we will be keep on using this word of feasible design. And of course, infeasible design does not meet one or more of the requirements. In yesterday's class, we have taken one example and one problem, both we did yesterday. One example in the form of a cantilever beam and problem in the form of a design of a can. When you just look at those two numerical problems, there you can see you can define the design variables, you can define the optimization function and optimization criteria, and you can formulate the constraints, and you can use those constraints for making the formulation. But one thing you should remember here is the design, what you will going to make or what you will going to system, what you will going to design. It should meet and it should satisfy all the requirements. All the requirements should be satisfied. If you have 2 or 3 requirements that need to be satisfied, and if you design, and if that design does not meet any one of your requirements, then it will be considered as an infeasible design. So yesterday we were talking about design of a cantilever beam, where we have a set of requirements that needs to be satisfied. One is the system should not fail under normal loading, and the deflection should not exceed some value. And also another two dimensional requirements. One is width should lie between so and so value, and the thickness should so lie between so and so value. So this is why they have given here is requirements are the one which will go into used for performance. And if those requirements cannot be satisfied or not able to meet, then design will not be accepted. So therefore, all the requirements what we are going to state in the problem formulation that needs to be satisfied by the design what we are going to make. Therefore, the feasible design and infeasible design. So these are the two important words quite commonly we will be using in our design optimization class. Next comes equality and inequality constraints. I think yesterday I was just highlighted this word when I was discussing the design of a can, equality and inequality constraints. The design problems may have equality as well as inequality constraints. The problem description should be studied carefully to determine which requirements needs to be formulated as equalities and which ones as inequalities. Yesterday I was when we are solving one problem on design of a can. I think I just stressed this in the when I was just discussing the solution for the design of a can. One important thing is what they have given. You have to design a can to hold at least 400 ml of liquid. At least 400 ml. So at least means the inequality comes into the picture. At least means at least the design of the can, the volume, the capacity of the can should be minimum 400 ml. Means it should be more than that also, but it should not be less than that. Equal to that or greater than that is the word at least. At least when it comes, it should refers to the inequality. If I put the same requirement in a different form, design a can for holding a liquid for 400 ml. Look at that. Design a can for holding 400 ml of liquid. Not at least. The word at least is not there. Only 400 ml means you have to design the can to hold only 400 ml. Not less than that, not more than that. Means the volume of the can what you design, it should be equal to 400 ml. So this is how we will go into identify the inequality and inequality. See, if the word at least is there, then it should lead to the inequalities. And if the word at least is not there, if you say it is capacity equal to the capacity, then it becomes to the equality. So you should be very careful, and you have to study the problem description very carefully while you are formulating or while you are formulating the constraints and design variables, right? For example, let us take another one example I just noted in the slide there. A machine component may be required to move precisely by delta to perform the desired operation, so that we must treat this as an inequality constraint. May be required to move precisely by delta. So it is to move this much, that's it. Feasible design must satisfy precisely all equality constraints. Also, most design problems have inequality constraints, sometimes called unilateral or one-sided constraints. So, in yesterday's class, with the design of a cantilever or a design of a can, so you can observe width, the range we have given. The width should be 3.5 to 8 millimeters or something like that. It will have two-way constraints, two-way values. on both the sides. The range we have given minimum and the maximum. That's why I told you there are that corresponds to the two constraints. And similarly for the thickness also. So it will have a range of values on either side, the minimum side as well as on the maximum side. So again, we will go to consider it as a two constraint. So one important thing, what a feasible design. When you say a feasible design, it must satisfy precisely all equality constraints. So therefore, almost design problems have inequality constraints. Sometimes they called unilateral or one-sided constraints. Note that feasible region with respect to an inequality constraints is much larger than with respect to the some constraints expressed as inequality. So this is regarding equality and inequality constraints. Hope you can make have a clear idea regarding what is inequality and what is equality. And the most important thing is whenever the problem description has been given, you need to study that carefully and you need to determine which requirements needs to be formulated as equalities and which one should be an inequality. Okay. See, hello, my dear students, can you hear me?
Yes, sir.
Yeah, any clarification, please stop me. Okay. So I will give a time at the last 5-10 minutes because I will be muting everybody because there are so many disturbances for me. And at the end, I will give you a time so you can just, if any clarification and any doubts is there, you can give me. I'm just muting everybody's. Okay.
Okay.
Yes, sir.
Yeah, another one important thing here is implicit constraints. Some constraints are quite simple, such as smallest and uh, largest allowable values for the design variables, whereas some complex ones might be indirectly influenced by the design variables. So this is the one important thing what you should remember when you are getting a solution for, or when you are just formulating a problem for optimization problems in design. See, some constraints you will find very simple, maybe smallest and the largest allowable values for the design. But some constraints which will look very complex and which might be indirectly influenced by the design. For example, we have shown here, deflection at a point in the large structure depends on its design. However, it is impossible to express deflection as an expressed function of the design variable except for very simple structures. These are called implicit constraints. So what does it mean? See, when you say a design of a structure, the structure may be very simple or it might be a large structure, very simple structure and large structure. In the case of large structure, the deflection at a point, it is impossible to express deflection as an explicit function of the design variables except for very simple structures. These are called implicit constraints, where when you are expressing the constraints, you should be very careful because you are designing it for a larger structure or it is you are designing it for a very simple structures. Sometimes the implicit functions in the problem formulation not possible to formulate the problem functions explicitly in terms of design variables alone. Instead, we must use some intermediate variables in the problem formulation. In a sense, there are certain functions, implicit functions in the problem formulation, not possible to formulate the problem explicitly. So I will discuss these things in much more detail because it is just an introduction to these implicit constraints. When it comes for further classes, we will going to discuss it in much detail. can identify how which constraint will be taken it as an implicit function and which will be considered as an explicit constraint. Those things I will give you much more details in the further class. But remember here is, see, when we say an implicit function, so these constraints, implicit constraints, these constraints are indirectly influenced by the design variable. Not be there in the directly, they might be indirectly influenced by the design variable. So you need to identify and which will fall as a implicit constraint and which will fall as an explicit constraint. That I will go into detail much in further classes. Okay. Yeah, so this is what I wanted to have before I go for the next numerical problem. So just to have some more details, some more just exposure to the some of the points, what you're supposed to remember and supposed to be used in the further classes also. Okay. Here, I will take to the next problem here, second problem. So here, we are designing it for a minimum cost cylindrical tank design. Minimum cost cylindrical tank design. This is make a note of these things. So what is this project or problem description? Step 1. Design a minimum cost cylindrical tank closed at both ends to contain a fixed volume of fluid B. The cost is to be found depend directly on the area of the sheet metal. This problem looks similar to that of a design of a can yesterday what we discussed. But smaller changes because when you look at the problem description here, this small variations, small changes we can observe, deviation we can observe from the problem description in the design of a can. Design a minimum cost cylindrical tank closed at both ends to contain a fixed volume of fluid B. The cost is found to depend directly on the area of the sheet metal. Yep. Then second step is data and information collection. Let's see with the dollar cost per unit area of the sheet metal. Other data is given in the project. So data is not much, a very simple design what we're talking here. And data and information collection looks very simple. Only thing, let's see with the dollar cost. So we'll be discussing in terms of dollars per unit area of the sheet metal. Means per unit area, what is the cost of the sheet metal? It is we're taking it as a C. Step 3, definition of design variables. So same thing, design variables or the problems are identified as R and H. In yesterday's class, that's what I was talking about, the deviation from the previous example of the previous problem. This problem here is, so there we have taken diameter as the design variable. So here we are just changing it into a radius. Anything you can solve either with a diameter or with a radius, not an issue for us. But I just wanted to make in a different ways how you can approach and how you can formulate the problems in different ways. So either radius or a diameter does not matter for the solution. The only thing is you should learn how to take different ways of design variables. Defining a design variable is the most important thing. Okay. The design variable for the problem is identified as R is equal to radius of the tank, H is equal to height of the tank, and step 4, optimization criterion. The cost function for the problem is the dollar cost of the sheet metal for the tank. Total surface area of the sheet metal consisting of the end plates and cylinder is. So that's what I was talking about yesterday's class. Design of a can, same thing, A is equal to surface area 2 pi r square into 2 pi r into h. So can you just study if you have noted down the formula for surface area for a design of a can. So it looks similar, pi r square into 2 plus 2 pi r into h. Therefore, the cost function for the problem is given as f is equal to c. C surface area. C corresponds to the dollar cost per unit area of the shipment. So unit area, surface area is formalized to pi r square into h. That is a total surface area, total area of the sheet metal. Two sheet metal, so end plates and the cylinder. So this is a closed tank or closed cylinder. Similar to that what we discussed in yesterday's. Formula remains same, but surface area has been formulated in terms of radius rather than the diameter. So please note the changes for the previous problem and this problem. So there it was diameter, here it was a radius. So accordingly, I just changed the formula also here. And here we have taken C as the dollar cost per unit area of the sheet. Okay. So therefore, C multiplied by the area will go to form a cost function for us. The same thing we are not done in the previous one. So this is the way how we have this is what the problem description is very important. When the problem description has given clearly the clarity among the problem description, the rest of things are very simple, and you need to study the problem description clearly. And you need to identify how to formulate the functions, how to formulate the constraints, and how we can define the variables. These things has to be done through careful study of the problems. Right? This is the optimization criteria or a function, objective function is given as f is equal to c into the surface area of the sheet, the total surface area of the sheet. And the last one is formulation of constraints. The volume of the tank 2 pi r square h, it is you have to read it as a 2 pi square h, is required to be V. Therefore, pi r square into h is equal to V. Both the design variable R and H must be within some minimum and maximum values. Here, each and every step, please make the difference, make the deviations, note the changes, what we have discussed in the previous class and this class. Okay. So please note these things. It's very important for you. Both the design variables R and H must be within some minimum and maximum values, and H should be minimum. This problem quite similar to the CAN problem. The only difference in the volume constraints, their constraint is inequality and here is an equality. Look at those two differences. So there we have used as an inequality constraint. Here we have an equality constraints for the volume of the tank. There we have put the volume should be greater than or less than, greater than or equal to 400 ml. But here it is not there. You have to design the tank, design the cylindrical tank for the volume V only. This is what I was talking about, equality and inequality in the previous slides. Okay, so this is the formulation of a constraint. Then we have another one problem, minimum weight tubular column design. This is the diagram of the column. So column basically is a long column which can withstand the compressive load. Okay. So this tubular column design, so we can formulate in two different approaches, formulation 1 and formulation 2. So the diagrams what I have shown here with respect to the formulations, the two sections. One is taken in form of the mean radius 2r and the thickness, and the second formulation I have taken in the form of inner radius and outer radius. In two different ways you can formulate this minimum weight tubular column design. Okay, I will show it for one formulation, that is I will take it for mean radius 2r and t, and I request you people to do it for the second formulation in terms of Ri and R. That's what I told you to have the pen and worksheets with you now. Okay. So this is a column which is having a circular hollow circular cross section, and it is uh, subjected for a load P. This is just a line diagram of a column. Let us look at the problem description here. Straight columns are used as structural elements in civil, mechanical, aerospace, agricultural, and automotive structures. Many such applications can be observed in daily life. For example, street light pole or a traffic light post, a flag pole, a water tower support, a highway sign post, a power transmission pole. It is important to optimize the design of a straight column since it might be mass produced. The objective of this project is to design a minimum mass tubular column of length L supporting a load P without buckling or overstressing. The column is fixed at base and free at the top as shown in the figure. This type of structure is called as a cantilever column. So this is just a problem description what we are having here. And of course, we have the data and information. Data and information buckling load is also called critical load for the cantilever column is given by buckling load is equal to pi square AI by 4L square. I think this formula you might have studied in your strength of materials or mechanics of materials in the EG program. Buckling load formula for a column with other support conditions, different end formulas. Here I is the moment of inertia for the cross section of the column and E is the metric property modulus of elasticity. Note that the buckling load depends on the design of the column. It imposes a limit on the applied load, that is, the column fails. Column fails if the applied load exceeds the buckling load. The material stress sigma for the column is defined as P by A, where A is the cross-sectional area of the column. The material arousal stress under the axial load is sigma A, and the material density is. So these are all the data and information what you're supposed to obtain from anywhere. So any textbooks or anywhere these things will be available. So you can easily just note down the buckling load formulae and what are the different metal properties that needs to be obtained, required formulae for calculating many things. So cross section of the tubular column is shown in the figure. I have already shown the diagram. Many formulations for the design problems are possible depending on how the design variables are intended. So here the formulation 1 for column design. So here we have taken it as two formulations. First formulation is defining the design variables. In the first formulation, the design variables are identified. R is equal to mean radius of the column and T is the wall thickness. Assuming that the wall thickness is thin, or is radius is much greater than T, the metal cross-sectional area, Gaussian, and the moment of inertia. So the two formulas, A is equal to pi R into T, and I is equal to pi R cube into T. Optimization criteria, so you have to minimize the mass. Mass is equal to density into volume. So volume is L into A is equal to pi into R into T. Formulation of constraints. The first constraint is the stress should not exceed the material allowable stress sigma to avoid the material. This is expressed as inequality sigma A replaced with A by A and substituting for here. This is the one constraint what we have here. And column should not buckle under the applied load T, which implies that applied load should not exceed the buckling load. Using the given expression for the buckling load in equation here used, we have buckling load should be pi cube E R cube T by 4L square. So this is the buckling formula. These are all everything available in your textbook. Finally, the design variable R and T must be within the specified minimum and maximum value. So this is the constraints what we have. So what I want here is from your side, I want the formulation 2, the column design. Till here it is same, no change. Till here it is same. But only thing I want this formulation in terms of R0 and R. Wherever this R0 and RA should be introduced, please look at that and then get me the formula and get me solve this, and we will going to discuss that today. Okay? Hello?
Yes, yes, sir.
Danush, Sandesh,
Yes, sir.
can you hear me?
Yes, sir.
Okay, what you want is, I want the formulation should be done in with R naught and Rf. So wherever possible, you can change and you can do these things. Okay. Uh, I will discuss much more things in the later classes. Because some more problems are there. This is one of the most important problem what I want to discuss. Uh, Please look at this. Note down the formulae and how you can change these things. In your this one formula, we can do that later. Any queries and any clarifications, you can make it up.
Nothing.
Srinidhi, any clarification?
No, sir.
Mithun, are you there? Sandesh?
Yes, sir, I'm here.
Okay, please note it down. I'm just closing this presentation. I think it will be getting more for me also. Okay, we will discuss this in the next class. Okay, much more.
Yes,
Okay,
sir.
thank you. Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.